Hello everyone, my name is Ankur Das. I'm a graduate student at University of Kentucky. So today I'm going to talk about SU3 fermions in three-band graphene-like model, and I'll explain in detail what I mean by these exact words. And this work has been published in 2019, and I've done this work with Dr. Sumiran Pujari, who's a faculty at Indian Institute of Technology, Bombay. And we have some future prospects of this project, and I'll talk about those motivations and how this project is related to other things. So just to motivate this problem, why we are interested in some question like this, is that the geometry of bands have been a very interesting topic for many years and have shaped many questions that we try to understand, including topological insulators, semi-metals, quantum Hall effect, topological defects. And the good examples of that is Dirac cones in honeycomb lattice, quadratic band touching in Bernal stack graphene, and so on and so forth. So we know that we can have very interesting physical consequences of these models, like suppression of backscattering, Klein tunneling, and quantum Hall effect, for example. So one way to understand this is that these Dirac points actually contribute pi or minus pi winding of very phase. And one other question is that why it can be pi. So this is a very simple example, which is for Dirac cone, is that you can solve this problem exactly and calculate what the Dirac points are by just calculating the limit of the log of the inner product. And this is just a picture, and you can draw this angular these angles of the states in a very simple way, and you can see that it fans out in a circle. So the natural question is how to go beyond pi, and it turns out that you can do something using more than two bands, and that's what we're going to discuss about. So we're going to use more than two bands, and any gap Dirac cone can have pi, can enclose any fraction of pi, but that's not what you're looking for. You're looking for some protected degeneracies, and we're going to talk about what these degeneracies mean and how they're going to behave. So this is a simple case. You can write down a Hamiltonian like this, and this is essentially the B dot S problem, again defined by Berry, which is basically spin 1 problem. And we know that the different Berry phases is 0 mod 2, and that is exactly what you find. There's nothing special about it, but we can write down some other models which look something like this, and this model has a very special behavior. So as you can see that in this model, the degeneracies are not only at the point, but there are line degeneracies coming out from that point. So there are line degeneracies always from this model. And the question is that what is the line degeneracies, what they mean, and how we can understand them. For obviously we cannot draw a circle anymore, obviously, because these bands intersect, so there's no gapped state, so we cannot calculate a Berry phase. And just to point out that triple point degeneracies has been in study for some time now, and people have done it mostly in 3D, a little bit in 2D, but mostly is, as we previously saw, the SU2 spin 1 model, which is writing a B dot S model with the spin 1 problem. But there is exception, and in 3D you can exactly see this kind of light degeneracies and they're called as nexus fermions. So the examples are given in our reference in 29, which is a cited paper, and this is the references if you want to look in future. But there are some precursors work have been Brillouin and company done in 2015. All are connected to this story of nexus fermions, where they have triple point degeneracies and line degeneracies coming out from them. This is what the standard argument is. So basically the argument is that if you quantify or classify a wild semi-metal, then you need to draw a sphere around it and calculate the total Chern number of that sphere, and that tells you that the Chern number tells you that the classification of this problem. But what I am trying to explain here is that, as you can see, in our case there is a beyond Dirac in 2D, because these arrow plots, as you see, doesn't close on itself. So what's going on and how to arrange that? So what we learned from our calculation that these bands are actually intertwined. So the right way to think about it is that if you follow adiabatically these bands, it will just cross from one band to another, and we have exemplified with the other version of it, where you can think of it as just the extended triangular lattice, and it's just band zone folded. There's nothing special about the second picture, but in the first picture these are actually intertwined band. You cannot think them as separate bands, and we can solve the solutions, and we can see the eigenvectors and the eigenvalues, if you write in a analytic form, are not analytic anymore. These are non-analytic functions. So this non-analyticity forces us to define a Riemann surface, and in that Riemann surface we are going to write down this 3 Riemann surface. We are going to write down these states, where one state will become another state as we go along the path. So this table is what we call our contribution, is that to come back to the original system, which means that every pair of eigenvalue eigenvector comes back to itself. You cannot go around around that point, the triple degenerate point, once, but you have to go thrice. And the Hamiltonian also comes back to itself 3 times. But what is interesting is that the vector comes back to it twice. As you can see, it's a 2 theta by 3 form. And that we have calculated for all different 3-band problems or 2-band problems that we can do. And you can see that in this classification, this winding number actually classifies all possible situations. Okay, and let's see that we can. This is the whole point of this story. But we can go beyond that. We can actually ask that: is it possible to write down something like a lattice model where this happens? And indeed, we set up that these are the lattice symmetries, and we break the CT symmetry and classified what kind of transformations there are. I'm not going into the details, and they're all present in our paper in a much more elaborated way. But basically, you can restrict our Hamiltonian into a much simpler form. And in this simple form, you can show that at the linear order, there are many possibilities. But one possibility where this line degeneracy exists is a fine-tuned possibility, but it does exist. So it's not protected, it's fine-tuned. But even though there is a fine-tuning there, it doesn't mean that these bands are completely cannot be classified. And the most general picture is this, where there are 2 Dirac points connected by a line degeneracy in between them. Okay, so this is the Hamiltonian, and we have shown the hopping Hamiltonian problem here, and also these are the band structure, just to clarify the things. And it turns out that this 3 degeneracy, we can use these ideas which we are working on, and hopefully that paper will come out soon. But basically, tungsten carbide system have this problem where you have these line degeneracies coming out from the triple degenerate point. So as you can see here in this picture, and the idea is that the idea that people have used till now is to identify the line degeneracies, but there is no understanding of how to classify these triple point degeneracies. And this is what the current situation is. We hope that our study will be able to shed some light on ideas by using the continuation Riemann surface analysis. So just to point out what the main takeaway to the relevance of 3D is that every cuts on that 3D, which cuts that line degeneracy, we can understand them very clearly. We have given the table, let me go back quickly to show you that table again, is that this table have classify all possible line degeneracies, at least in 3-band model. And even if these bands cannot be classified, we can understand the 2D. And to just point out, in 2D, Brillouin material have exactly our lattice. So we want to understand how this analytic movement in the geometric space we can use to understand these band structures, how to classify this band structure using analytic continuation. That is the key point here. And in 2D, we have seen that the analytical continuation actually allows us to wind thrice and come back to itself. And we can write down a non-abelian geometry, and I don't want to go into this, but there is some non-abelian way to understand it, but not very special. And we can calculate the Hofstadter butterfly. As you can see, it's a very nice picture. It has 1/12th repetition, because the smallest in our hopping system, the smallest unit cell is 1/12th of the honeycomb unit cell. And you can see that it has some time reversal. If the time reversal is not broken, which is exactly the half flux per smallest unit cell or smallest hopping area, is that it's still gapless. There is no gap there. Okay. But there is something interesting. You can try to ask that what are the quantum orbits there. So as we have shown that in general, the most general case is like this. So this is the general case I'm trying to understand. So in this general case, you can see that the bottom band actually behaves like quadratic n, but the top part is actually also quantized, but we can calculate what this quantization is, and it turns out to be 7/9, something in between, and that is coming from these weird quantum orbits or electron orbits in the momentum space, the equal energy orbits. And these are the conclusions. So basically, you can go to our paper, and there are details of this paper. And we read down a toy model, which is beyond-Dirac fermion. These are fine-tuned models. These are not protected, but still they show that bands can be beyond Dirac, and you may not be able to classify them immediately. And we showed that the wave function geometry is explicit, and they are understood by analytic continuation of the wave function and the eigenenergies. And there is a 3D nexus fermion picture in the 3D, which we want to understand in future. So there are physical properties, effect of interaction. These are all new questions that we'd like to understand in future. These are the acknowledgements, Dr. Murthy and Dr. Santos, and we thank the funding agencies, and thank you very much.